Hello, everybody. Today I'm going to talk to you about my research, which has briefly been mentioned already, but it involves development of an MRI technique to allow for quantification of two contrast agents simultaneously. Before I get into that, I'm going to talk about the motivation behind this. Obviously, Kim has kind of already covered a little bit of this. So as Kim kind of just showed, immune systems, highly complicated. And so interactions with immunotherapies, as a result, are also complicated. This means that the more data that we can provide about the inner workings of immunotherapy during its application and development, the greater our understanding, which can further treatment development and optimizations. However, we are currently limited, as MRI can only currently quantify one contrast agent at a time. And we can circumvent this by the introduction of additional cohorts or specialized hardware, perhaps duplicating scans. But in the end, studies of immunotherapies would greatly be aided by an MR technique, which could quantify multiple contrast agents at once. And so here's an example of a study, one of the ones that Kim showed, but basically two different mice were shown two different processes. It would have been more valuable to have them on a single mouse. And that's kind of the aim of what we're doing here. And so the reason that this is difficult, as previously mentioned, is that if we include a second contrast agent, one parameter map is no longer sufficient to measure either one of these agents. And we can overcome this if we have a technique which provides multiple parameter maps, and more importantly, multiple parameter maps at the same time. And so the goal of my research is to develop such a technique, which allows for multi-contrast MRI within an in vivo appropriate time frame. And of particular importance to our lab is that this technique be also T2 star sensitive to allow for quantification of iron-labeled cells. And so when looking for an initial sequence to base this research on, MR fingerprinting immediately jumped out to us, as it is known for providing multiple parameter maps within a single scan. MR fingerprinting was a hot topic in the MRI community about 5 years ago. But for those of you unfamiliar, unlike a traditional MRI sequence, which seeks to drive the system into a steady state, MRF lets magnetization evolve with time, resulting in data being a series of voxels with a rapidly changing signal. The signal evolution is performed by variation of the sequence parameters, such as repetition time and flip angle, in a known yet pseudo-random way. And we refer to this signal output, each of them, as fingerprints, and while each one of them is indicative of the underlying properties of the tissue from the voxel that it came from, it by itself is useless. Luckily, the evolution of bulk magnetization in an external field is mathematically well-defined, both by the block equations and for non-balanced sequences, extended phase graphing. And so this allows for a simulation of a database of all expected tissue types to be created, commonly referred to as a dictionary. By matching this dictionary to the fingerprints, information pertaining to each voxel can be located within the database. And this is kind of analogous to how with traditional fingerprinting scanners, you just use the pattern of a thumb to locate much more information about an individual. And so one of MR fingerprinting's most promising features is that this technique is tremendously robust to undersampling, allowing for extreme acceleration under the right conditions. And so traditional MRF was developed in our system, which we then modified to be a non-balanced steady-state pre-procession sequence, allowing us to ignore off-resonance calculations and allow for T2 star variation space within the dictionary. And then we implemented a variable density spiral trajectory to enable more robust undersampling, which included sections of the sequence that you can see in the center here, which have zero flip angle to improve our T1 accuracy. And then to include T2 star sensitivity, which is the novel part of this, we introduced TE variation on the end of the sequence. And all of this culminates in a sequence which, when fully sampled, can image a single slice in about 28 minutes. But it should be noted that this is still probably highly undersamplable. And so our first task is to check out how much data of this we didn't need to still provide accurate parameter maps. Preliminary data showed that despite our modifications, our version of MRF remained highly robust to undersampling. As you can see in the figure shown here, while a single frame of the collected signal becomes much more noisy when undersampling 8 times, the resulting parameter maps are almost completely unaffected, especially when correctly masked. And this trend continues when further increasing the undersample factor, with our initial attempts at T2 star MRF able to produce visually similar parameter maps accelerated up to 16 times. And we found that pushing past about 8 times undersampling did start to affect the root mean square error of the parameter maps, particularly in the case of R2 star or T2 star. So we chose to remain 8 times undersampling, which gives us a scan time of 3.5 minutes per slice. And so using the sequence, we were able to demonstrate dual contrast quantification. We built phantoms that contained both varying amounts of SBIO labeled cells and gadolinium, and demonstrated that we could separate the two contrast agents in vitro. And most importantly, we could do this very quickly. So it can be done almost 10 times faster than conventional methods, which is kind of the aim here, is to do it as quickly as possible so that it is appropriate in vivo. And so we did some in vivo tests, and our pilot in vivo data of the MRF with T2 star sensitivity shows promise, with a mouse receiving a subcutaneous injection of SBO labeled antigen in the right flank 2 weeks prior to imaging. MRF was able to show that R2 star maps show an increase at the site of injection, as well as showing similar robustness to undersampling as the in vitro results. However, 4 minutes per slice or 3.5 minutes per slice is still not fast enough if we want to provide kind of volumetric data. We want to collect several slices of this. It's going to take an hour. That's not good enough. And so we really want to push that time down to 15, 16 slices at about 25 minutes. And so it's necessary to look at how to further accelerate this sequence. Now, one way which MRF has been accelerated previously has been with sliding window reconstruction, where temporal data is traded off for spatial data by combining neighboring frames to provide less noisy images. However, while sliding window is compatible with traditional fingerprinting, we found that our modified T2 star sensitive MRF was prone to degradation while applying sliding window. And after further investigation, we found that beyond a certain window length of applied sliding window reconstruction, the TE modulated part of the MRF sequence that we kind of added on would not retain T2 star sensitivity. And so by developing a non-uniform sliding window, which is novel, I believe, where we apply a shorter window length over the T2 star sensitive region of the sequence, we're able to utilize the acceleration properties of the sliding window while retaining the T2 star sensitivity required. And you can see that in these figures here, the red is a standard sliding window, and the data is this is comparing the gold standard values of T1, T2, and T2 star to the output of the T2 star MRF. The red value is not good. It's not really lining up, but when we apply this non-uniform sliding window, we see the blue values start to kind of come back towards the values that we know are true. And so we can say that in this current implementation, the T2 star sensitive dual contrast MRF is working correctly and can accurately perform at 24 times undersampling, which puts us at about just over a minute per slice, much more in the region of where we need to be for in vivo application. And so just a quick summary of what I've kind of shown today. If we want multi-contrast MRI, we need to quickly produce simultaneous parameter maps. And we have modified MRF to include both T2 star sensitivity to allow one of these contrast agents to be SBIO, and accelerated the sequence to a point where it should be applicable in vivo. And obviously, the work is never done. So the final step of my research is going to be to prove that this works and validate it in vivo. And to that end, we'll be using the glioblastoma study with both GAD and SBIO contrast agents being present within the mouse. That is all I have for you today. Thank you very much for listening. I will take any questions.